Hello, vintage computer friends. Since I'm currently in the flow of quantifying, measuring the performance of all these educational computer systems on my YouTube channel, and I still have my oscilloscope on the workbench, I figured I continue and also present and measure the last educational computer system from my collection, and this is the Philips MasterLab. So a very interesting and very rare educational computer system. It was released, well, probably in 1984, and I think it's fair to say that it wasn't a commercial success. So it was released about a year after the Kosmos CP1 computer that we have already covered on my channel, together with the Busch Microtronic from 1981, as well as the Science Fair microcomputer trainer from 1976, which kind of, I would say, started that whole business of educational computer systems, mostly based on masked programmed microcontrollers for kids and juveniles, right? And so the Philips MasterLab is currently running a demo program here, and what you already see is, it is actually offering full control over the display. So, and as I said, unlike the other machines that we looked at, this is not running an emulated virtual machine language, right, in some kind of interpreter, but it's actually being programmed in native SCAMP3, SCMP3 SCAMP machine language, because the main CPU is an National Instrument 8070. So this is a big chip here. This is an 8-bit, microcontroller from National Instrument that was also released around 1976, 1977, similar time frame as the TMS 1000 series from Texas Instruments, which were used by the Science Fair microcomputer trainer and the Busch Microtronic, right? And this is a 4 megahertz crystal, so the machine is a native SCAMP3 microcomputer trainer clocked at 4 megahertz, and like the other machines, it also comes with a couple of demo programs, right? So currently we are running the text scrolling demo program. So here's a run stop button, and there are other demo programs, right? Some games, some blinking lights, and so on. So another game I can show you, they actually added a dedicated button just for launching the demo programs. So Spiele, it's in German for games, right? So demo programs. And another one is the scrolling LED light. And so interestingly, you see, you don't see the LEDs going on and off. So rather they have a switch here, which basically then toggles the outputs between the 7-segment LED display and the individual LEDs, right? So they're using the same output port for this. Kind of clever, right? And so you also see that you can achieve full control over the display, right? And what we really want to do is measure the performance, basically in terms of how many operations per second can this machine do, right? And we are going to use the oscilloscope again. We already know the clock speed is 4 megahertz, right? And so we are going to enter a program which toggles basically 1 bit toggles a bit on the output port, right? And in that regard, the machine is a little bit more, or let's say, much more limited than the other machines, right? So I would say that is kind of the weak point of the MasterLab, the number of output and input ports, right? So the machine does not have dedicated instructions for input-output, but rather there's a so-called status register S, which contains, for example, the flags, like something like the carry flag that is set by an overflow operation, right, arithmetic overflow, and also 3 user-definable flags that you can set basically in this status register, right? And so these are the three outputs here, F1, F2, F3, which also have dedicated LEDs here. There are also transistors to amplify this, so you can actually directly, here's the transistors, right? Something like a emitter follower, so you can directly connect a load to this, like a light bulb or so. So the outputs are able to drive this, but you only have three of those outputs, right? And then in terms of inputs, for digital inputs, we only have two inputs, SA and SB, and there are also dedicated buttons basically which you can use to toggle these input bits, right? And those are directly connected to the hardware basically, so whatever is basically currently presented to SA or SB directly shows up in the S register of the SCAMP3 of the 8070 CPU. So kind of interesting architecture, right? And completely different from what the Kosmos CP1 had. I mean, the Kosmos CP1 is really the clear winner in terms of sheer number of GPIO ports, right? And the Busch Microtronic had 4 output and 4 input as well. But these ports are going to be much faster, right? Because they are programmed in native machine language. So I think another little detail here, this machine actually has an on-off button, right? Which none of the on-off switch, which none of the other machines had. So when the machine starts up, the default address is at address 1000 for RAM. By the way, the machine has 1 kilobyte of RAM, right? So there are two 2114 SRAMs here, each having 512 bytes. So similar to the Microtronic, which actually has one of these 2114 SRAM chips for its memory. And then the SCAMP3, the 8070, is not mask programmed, right? But it actually has a real 2732 EEPROM here, 4 kilobytes, right? And then, you know, there's a little bit of glue logic, of course. Here you have a DIN socket for the cassette interface, right? And voltage regulator. And then here are the input-output ports, and the system also supplies 5 volts and ground, of course, for experiments. So you can connect basically the Philips experiments electronic kits to this. And interestingly, there's also, you know, the full CPU port available here, so for further extensions, and I don't think any of these extensions were released. The machine was commercially not a success because it was much too late on the market, right? 1984 was already too late for these kinds of machines, and the home computer revolution had already started with, you know, the Commodores and Ataris and the Amstrad CPCs and things like that. The MasterLab also has a very interesting creation history, right, how it came about. So it turns out that the Dutch multinational company Philips only provided the name to the whole series of science or experiment and electronic kits that they offered throughout the 1970s and 1980s, right? But officially, Philips had already retreated from the market of such experiment kits and science kits in the late 1960s, and from then on a company in Germany was responsible for developing the program, the company Schuko. There's also another company involved in that, right, that merged with Schuko, the company Mangold. And Mangold is actually the label that you find on some of the parts, right? For example, the power supply, Gamma, that stands for Mangold something, right? So that's the name of that company that merged with Schuko. And they supplied all the, they developed the series and also this computer. In particular, one person was responsible for the machine, and this is the person that also wrote the instruction manual, right? So very nice thick instruction manual here for the MasterLab, and the guy is called Erhard Meyer, right, who wrote the preamble to the system. And you also find his name in the ROM, right? So he also developed the firmware for this machine, the monitor program, etc. I'm not sure if he also developed the hardware, but it is likely because other sources mention him as a source for an expansion board for this machine, which was never released, right? So there's another enthusiast who provides a lot of very helpful and interesting information on his website, who then mentions that he acquired this expansion board directly from Erhard Meyer. So Erhard Meyer, if you're still around and you can illuminate the creation history of the Philips MasterLab, please reach out, and we would really like to, you know, document this more and unravel the mystery of its creation. The machine also had some academic blessings, similar to all of the other machines, right? So the Kosmos CP1 and the Busch Microtronic also had like professors that would then say, okay, that's a great machine for learning, right? You should really do that. And one more piece of history that's known is that this Erhard Meyer, who developed the firmware and wrote the manual, was working for an institute for teacher training, right? An institute that would basically coach and teach high school teachers to get up to date and up to speed with new technologies, right? Especially computer science and electronics and STEM education, right? Continued STEM education for high school teachers. And that institute was also in Hamburg, so it is known that Erhard Meyer worked in Hamburg for the Institute for High School teacher training, right? Alright, let me give you a little overview over the function buttons here on the right, the blue buttons, right? We already looked at the Spiele button for starting ROM programs like SP0, for example, is the scrolling text demo. RS is for reset, of course. And then you can inspect the CPU registers by using CPU and then a number for the register, right? 0 is, for example, the program counter. CPU 1 is the stack pointer, so this machine actually has a stack. CPU 6 is the accumulator, most importantly. CPU 7 is the extra register, and you can combine A and E into a 16-bit register for addition and multiplication and arithmetic operations like that. CPU 5 is the status register, right? So that contains the flags, especially the carry overflow flag, as well as these flags for the input-output ports that I mentioned, right? So we are going to actually write values into the into this S, the status flag register, in order to toggle the output port. And then there is a load button and a save button for cassette operations, the run button for starting the program, and with the AD button you toggle between address input and data input, right, at this address. And there's a little indicator here, a marker, visual marker. If it points to the right, then you are actually entering the address, right? Like so. And programs always start at 1000. And if it points to the left, like so, then you are entering the opcode, right? So that's a good way of doing that, right? And I also like the visual indicator and that you save a button that way. So yeah, and then you can basically increment and decrement the current monitor address, right? Okay. Alright, let us enter the program now that will produce the square wave at output F2 that we can then measure with the oscilloscope. So when you fire up the machine, well, it greets you by saying hello. And then the next thing you do is you push this AD button in order to enter your program, and programs start at address 1000. This is where the RAM is, right? So first we want to load the accumulator with a certain bit pattern, and that bit pattern will have set the output bit for output F2 to 1. So the opcode for loading the accumulator is C4, explosive thing, right? So C4, and then we increment the address, and the operand is 4, and that's because the output bit for F2 is bit number 2, right? So if you count from 0 0, 1, 2, second bit or the third bit, right? But the decimal value of this bit is 4. Okay, now we have 4 loaded in the accumulator. Now we need to bring the accumulator into the status register, right? Because the status register directly maps to the outputs, as well as you use the status register for reading the current state of the inputs. So the inputs here as A, as B are of course only read-only, but you can write the output bits, right? So, and in order to now copy the load the status register with the accumulator value that we put in there with 4, we use the opcode 7, right? 7 means load status register from A register, from the accumulator. And now we want to toggle basically the value. So now we have the 1 basically output at F2. And now we want to reset, set that bit back to 0. So we toggle it again, we load now the accumulator. This time we want to load 0 into the accumulator. And then again we need to output it into the S register so that the port will be updated, right? Okay, now all that's left to do is a jump. And an unconditional jump has opcode 24. And interestingly now, it's a little endian, right? So you first specify the low byte of the address, right? And you have to subtract 1 also from the address. So if you want to jump to address 1000, right, you actually need to jump to 0FFF, so 1000 minus 1 in hexadecimal, right? So we need to specify FF here, and now 0F, right? Okay, and now the program is in memory. We can also check it one more time. Load accumulator with 4. Load S register from accumulator, bring the 1 value to the output, right? Load 0 into the accumulator, again update the output port, right? And then jump back to 0FFF, so that means it jumps back to address 1000. And now we are ready to run this program, and let's see what we get on the oscilloscope. Alright, so there we have our square wave. And what does it say? It actually says 29.4 kilohertz. Wow, yeah, that's really fast. And now we can multiply this again by the number of instructions that we needed in order to implement this program to get an estimate for the instructions that it can compute by seconds, right? So we actually needed how many instructions? 1, 2, 3, 4, 5, right? So if we multiply 29.41 times 5, we are getting 147,000 instructions per kilohertz, right? Sorry, per second. So 147,000 instructions per second. I think we have a clear winner here, and in terms of previous performance, you know, all the machines are basically a joke, of course, in comparison to this machine. But I mean, it also has its limitations, right? In particular, the number of only 3 output ports and only 2 input ports, right, is kind of limiting for all kinds of physical computing experiments that require more input-output, right? And I think this might have been the idea of this additional expansion port here, which would have allowed you to extend the hardware capabilities of the machine significantly. Yeah, so at some point I want to do a deep dive video and explain a little bit more about the machine, right, and SCAMP3 programming. But for now, that's it. Thanks for watching and stay tuned. Until next time, right? Bye. Take care.